Sometimes the world isn't just yes or no. How do we add a bit of nuance to our two-class classifiers? Welcome to this video on classification. My name is Kevin Fiesel, and I am the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. I have spent the vast majority of this video series covering two-class classification scenarios, and there are good reasons to do so. Specifically, I'm going to give you 3 of those reasons. First, two-class classification is easy to understand. The algorithms are fairly simple, and we can take advantage of the assumption that if it isn't Class A, it's got to be Class B. Second, two-class classification is really common. You may express a bit of data science bravado and exclaim that, no, your situations are so complex and nuanced, unlike the rest of the world, that we couldn't possibly limit ourselves to 2 options like that. But the reality check is we do it all the time. And the third reason I started with the two-class classification scenario is some algorithms require having just 2 classes. Think back to logistic regression. We're drawing a sigmoid function where we have data clustering around 0 or 1, or -1 and 1 if you're one of those types. We don't have a third place toward which data points can gravitate, so we can only express things in terms of 2 classes. It's similar with online passive-aggressive algorithms. We have a margin defining our 2 camps, but we can only have 2 camps. Never fear, however, for there are ways around this challenge. 2 of them, in fact. First, some algorithms can naturally support more than 2 classes. Anything built on decision trees like CART, Random Forest, XGBoost, LightGBM, these can natively support more than 2 classes. If you think about it, the controlling factor for our decision tree is simply that we make a decision for each terminal node. But we could potentially have as many unique classes as we have terminal nodes, and nothing about the algorithm would change. Similarly, k-nearest neighbors and naive Bayes natively support more than 2 classes as well. We focused on a pair of 2-class scenarios to let us make fair comparisons across the board, but these can scale out to multiple classes with no problem. And for algorithms that require exactly 2 classes, we have a neat trick. We can perform something called one versus all comparisons. The idea is simple. Suppose that I have 3 classes, A, B, and C. I would like to predict the probability of each class being the correct class given some set of inputs. But if I'm using logistic regression, I can't do that. I have one too many classes. So instead, let's rephrase this a different way. The probability of a given class versus the probability of all other classes without distinction. Now I have 3 separate comparisons. The probability of getting A versus the probability of getting something other than A. The probability of getting B versus the probability of getting something other than B. And the probability of getting C versus the probability of getting something other than C, given my input criteria of X. What's nice about this is that, for purposes of comparison, these 2 ideas match up, and we can find which of the 3 operations nets us the highest probability given our input X. In this case, let's suppose that C returns the highest probability, so we select it, which makes perfect sense because when in doubt, Charlie out. And that's really all there is to know about multi-class classification. Well, that and the details of the confusion matrix that we covered in a prior video. Because I've already spent a fair amount of time covering that scenario, I don't need to belabor it here. Instead, let's go to the demo and check out multi-class classification in Python. This will be the final notebook in our series, but it's a doozy. In this notebook, we are going to focus on multi-class classification, and I will include a wide variety of algorithms. Let's first run these import statements, bringing in our normal libraries as well as matplotlib. I'm also going to set up the dots per inch on each figure to 100, so that they'll show up well on this screen. The data set I'm going to use is a set of measurements around dry beans. As I scroll through the features, we can see that it's a nice and clean data set. Everything is already a numeric feature, and we're not missing any data. We have 13,611 rows and 16 features. Scrolling all the way to the right, we have our class of bean. We can only see 2 of those here, but I will note there are several classes, as we will soon see. Our pre-processing will also be quite simple. The Y attribute is class, and everything else remains in X. We'll take 30% of the data for testing purposes, saving 70% for training, and I'll use random state 1740 for this. The percentages I've chosen are a bit arbitrary, sure, but they won't negatively affect results. Now it's time for the throwdown we've been waiting for. First up, we'll look at CART. I don't have any real commentary around this technique because we did a video on CART already, so this is a bit perfunctory. As I run this, our accuracy is 89.4%, which seems pretty good. Now let's look at the confusion matrix. scikit-learn has a nice way of displaying multi-class scenarios called confusion matrix display. It generates a matplotlib image, which we'll show on the screen with the plot method. This shows that we have 7 total classes of dry beans, which we see as 0 through 6 in the image. To interpret this image, we have a diagonal running from the top left to the bottom right, and that represents correct predictions of test data. So of the times we predicted class 0, we got 318 of those right. Of the times we predicted class 1, we got 174 of those right, and so on. Reading from left to right, we have instances of a true label and what we predicted. The top left cell has 318, meaning we predicted class 0 and it was really class 0. Moving over 2 boxes, we have 25 instances in which we predicted class 2, but it was really class 0. We have 4 times where we predicted class 4 and it was really class 0, 2 times when we predicted class 5 and it was actually class 0, and 8 times where we predicted class 6, but it was class 0. If we look at a vertical slice, this tells us how we did on predictions. Looking at the slice in the middle, that represents predictions of class 3. There were 0 cases of a bean actually being in classes 0, 1, or 2 when we predicted 3. When we predicted 3, it was in fact class 3 924 times. When we predicted class 3, the bean was actually class 4 9 times. Similarly, we have 28 cases where the actual class was 5 despite us predicting 3, and 74 cases where the actual bean was class 6, but we predicted class 3. On the whole, this chart looks pretty good, which makes sense considering that we did get nearly 90% of predictions right. It seems like there's a bit of confusion with classes 3 and 6, as those interactions were where we saw the most errors. 74 times when we predicted class 3, but it was really class 6, and 110 times where we predicted class 6, but it was actually class 3. If I print out the classification report, we can see the actual labels of those classes, as well as our precision, recall, and F1 score for each. We can see that class 0 is Barbunya, class 1 is Bombay, and so on through Sierra as class 6. Based solely on CART, the matrix shows us that it seems Barbunya and Cali beans are pretty similar to each other physically, and Dermison and Sierra are very similar to each other. It also looks like Bombay beans are different enough from everything else that we almost never get those predictions wrong. But let's see how other algorithms shake out. Next up is random forest. Just as with CART, we're going to run the algorithm with a minimum of ceremony. We could spend some time tuning hyperparameters to tweak the results a bit, but we already have an accuracy of 93.0%, which is a boost on CART. If I show the confusion matrix, we see a set of results similar to CART. Dermison and Sierra are the 2 types of beans we're getting confused the most frequently, and the rest of the errors are quite small in terms of magnitude. This leads us to our classification report. Our top line accuracy is 93.0%, and each of our F1 scores is at least 89%, with most at or above 92%. Telling us that we have a fairly balanced data set, but that random forest had a little bit of trouble distinguishing Sierra from Dermison. XGBoost is our third algorithm. It does require numeric labels, so we do need to encode this label. I've developed what I'm calling a rickety encoder. It is a bit janky, I'll admit, but it does the job well enough while still retaining the same information that we have in the other graphs. For XGBoost, I did tweak the parameters a bit and landed on a max depth of 9 levels and 300 estimators. Note that I have set the use label encoder parameter to false, as we've performed our own label encoding. And the accuracy of this is 93.3%, even better than what we had for random forest. Before I show the graphs, I also need to decode my data, so of course I'll need a rickety decoder. Then I can load that into the confusion matrix display. The chart looks substantially similar to the first two, except that our diagonal is just a little bit better. We can see that the biggest pain point is still the intersection of Sierra and Dermison, responsible for 131 of our total of 273 errors. Sierra is still a tough nut to crack, old bean. Now let's look at K nearest neighbors. I've set the neighbor count to 5, and I will note that increasing the count of K makes accuracy marginally worse. Our overall accuracy is 72.6%, which is pretty bad. If we look at the confusion matrix, we can see errors all over the place. This is a mess, and I believe the reason why is the curse of dimensionality. With so many different input features, we're getting hung up on insubstantial differences that pull beans out of one cluster and into another. The classification report substantiates the mess that our eyes see, telling us the F1 score of Barbunya dropped to 0.51, so everything other than Bombay suffered. Like I said, I think the problem here is the curse of dimensionality. Fortunately, there is a way we can test this, and that is by using principal component analysis, or PCA. PCA allows us to extract meaningful variance from a large number of dimensions, that is, from a large number of features, and describe most of the variance in terms of a small number of dimensions. I don't have any meetings to attend right at this moment, so let's spend a little time and give it a try. The first thing I'll do is import the standard scalar class from scikit-learn. I'm going to resize each of our input features based on this standard scalar. The reason I want to do this is to make sure that features all have roughly the same numeric range, maybe -3 to +3 or thereabouts, versus having one feature range from 0 to 1 and another range from 0 to 1,000,000, because the latter can overwhelm the former in a principal components analysis. Next, I'll import PCA from scikit-learn's decomposition namespace. We'll perform PCA and gather the top 3 components. 3 is a bit of an arbitrary choice that I made, but typically I like to start with either 2 or 3 as my number of components. We'll fit the results and call that PC_beans for the principal components of our bean measurements. If I view the data, I can see an array with just 3 components, which is exactly what I wanted. Now I can split this data into training and test datasets using the same random state and test size. I might not get exactly the same values in my training and test datasets as I did pre-PCA, but at the very least it'll be close enough for us to work with. Let's run the analysis again. This time I've set the number of neighbors to 101, because Dalmatians. As I do mention in the note, 101 is a bit high of a number, and honestly, it's not one I would seriously consider in an actual application. Granted, we do have over 9,000 records in our training data, so 101 is still a relatively small percentage of the total training data set. And it also turns out to be one of a good-sized set of numbers that maximizes accuracy, though realistically, if I set into 23, it's about 1/10 of a percentage point lower, yet it's a much more reasonable number for neighbors. Regardless, as we run this, with 101 Dalmatians, we get 89.2% accuracy. That's still not great, considering it's basically the same as what we get with CART, but it is way better than what we initially saw. The confusion matrix also looks more reasonable, though we do see an interesting dilemma. The Sierra and Dermison problem is still there, and it's at about the same level as we see for most of these algorithms. But there's also a bigger problem between Barbunya and Kali than we had in our tree-based algorithms. So it seems that the drop-off in accuracy is almost entirely due to this mix-up. We could also experiment with other numbers of principal components and try to tweak the process in other ways, but I will leave that as an experiment to you, dear viewer. Now let's take a look at logistic regression. I'm going to kick this thing off and set the maximum number of iterations to 10,000. Unfortunately, that does mean we'll be spinning our wheels here for a bit, but when we do eventually finish the task, we will get back an accuracy value that is somewhere in the neighborhood of 92.1%. That will put us right in the mix of things. It'll sit higher than CART or the PCA enhanced K nearest neighbors, but be just a little bit worse than random forest and XGBoost. If we look at the confusion matrix, we're going to see the same patterns, showing a challenge with separating out Dermison and Syrah beans. The classification report isn't quite as nice as what we saw for random forest or XGBoost, but it is still pretty solid overall. Next, let's look at an appropriate form of naive Bayes. In the video I dedicated to naive Bayes, I used the categorical NB form. This time around, I'm going to use multinomial NB because that's the variant that works best for all numeric data like what we have. I'll enable Laplace smoothing and generate some predictions. We can see an accuracy of 79.7%, which is bad. Looking at the confusion matrix, we see familiar error points, but also a real problem across the board with Syrah, and a big problem separating Barbunya and Kali. I could try against the PCA dataset, but one thing about multinomial naive Bayes is that all of the values need to be positive. Yeah, I could tweak the X values to ensure that everything is positive, but we're not going to unlock any massive gains with it this time around, so I'll skip that and move on to online passive-aggressive algorithms. We'll use the passive-aggressive classifier with a max of 3,000 iterations and our normal random state. And the results are abysmal. An accuracy of 46% is not something you probably had on your bingo card. Let's take a look at the confusion matrix. The problem we're seeing is that we are almost exclusively predicting Dermison and Syrah beans, and we're getting it wrong a lot. This is where online passive-aggressive gets a bit funky. It's not necessarily a great multi-class classifier. The classification report does help us finish up the story. We have 0 predictions of Horos or Seker, and we do poorly on every single one of these classes. But what if I used the PCA dataset that we tried for K nearest neighbors? In that case, the accuracy shoots up to 70.7%, which is still way worse than anything else. The confusion matrix shows us that we are back to predicting Horos and Seker, and we actually do a pretty good job of it. But we have 0 predictions for Bombay, meaning that PCA with 3 components seems to have lost some of that uniqueness for Bombay. The classification report finishes our autopsy of this passive-aggressive algorithm. Horos and Seker have F1 scores over 0.9, which puts them in spitting distance of what every other algorithm can do. But for the rest of these, we're in bad shape. The moral of the story here is, don't limit yourself to just one classifier. If we came in assuming that naive Bayes, for example, was the best choice for the job, well, we'd end up with a well below standard result. So give the whole series a try. That was our overview of multi-class classification. As we saw, in practice, implementation is very similar to 2-class classification, even for algorithms like logistic regression or online passive-aggressive algorithms, which natively support only 2 classes. The next video will wrap up this series. In it, I'll give you some tips around when to use each classification algorithm and when it might not make sense. We'll have links and show notes in the description below. And until we see each other in the next video, take care.